Hey, hello, welcome to Advanced Algebra 2. We're in the 11th learning target, the second part, and we're going to continue to talk about function inverses. Oh man, that XY swap is amazing. Okay, so now we're going to take it from a general idea of what an inverse is and apply it to exponential functions. We've had a lot of practice with exponential function graphs. And so we're going to go ahead and do that. Now this first example says graph y equals 2 to the x plus 2 minus 3 and its inverse. Okay, so we'll graph the function first. So you graph the function, it's there, and so you're like, okay, I got a horizontal asymptote down at -3, so I'm going to draw that, and you may not draw it, that's just fine, as long as you know it's there. So then you've got to do the points, right? So like, that's 2 to the x plus 2 minus 3. You're doing each of the points from a normal 2 to the x graph. You move them left 2 and then down 3. And that's your graph. That's not terribly exciting. And if you want help with that, I can always help you individually. But that's, that's the thing. Okay, now we're going to make the inverse. Now, for the inverse, you see how the original graph had a horizontal asymptote at -3? Well, the inverse has a vertical asymptote at -3 because the x's and the y's swap. Wow, okay, so now you got that. Now you take the points. So let's see, we've got a point at 0, 1, which means for the inverse, we'll have a point at 1, 0. And then, let's see here, we got a point at 1, 5 on the original function, so 5, 1. And then, kind of adorably in this case, the original graph has a point at -1, -1. So for the inverse, that turns around to being the same points. And then the original graph also has a point at -2, -2, which, that you turn that around, and that's still -2, -2. So there's the graph of that. All the x and y points have been swapped, and then you've got a graph. And instead of the graph dying toward the horizontal asymptote, the graph kind of dies toward the vertical asymptote, and there we have it. That's interesting. The next part of the example says, determine the inverse symbolically. You know what? I actually forgot to do that. We're gonna do that later in class. So we're going to move on to the second sentence, which says make intelligent comments regarding domain, range, asymptotes, and intercepts. Okay, so the original function, its domain is all real numbers. It's an exponential graph. It goes left forever. It goes right forever. It's happy-go-lucky kind of guy. The range is not all reals because it starts, well, extremely close to the horizontal asymptote. So it starts close to -3 and goes up to infinity. And then we've got the asymptote, and the asymptote is that line y equals -3. So there's that. And then, let's see here. We need a y-intercept. Now the y-intercept is not that bad, really, because you look at the dot there. We happen to have the point 0, 1. Of course, you could always stick in 0 for x if you're feeling insecure. And then for the x-intercept, oh gosh, golly gee, that's not going to be pretty. We have real work to do. Okay, so you make the equation equal to 0, and then you're going to solve by adding 3. So you have 3 equals 2 to the x plus 2. This is stuff you should be familiar with, but it's always good to practice occasionally. So it's log base 2 of 3 equals x plus 2. Remember, when you do the logs, the equation kind of shifts around in the wrong way. And then so x is log base 2 of 3 minus 2, which is true but not helpful for most of us with our calculators. So I'm going to change the base to e, so it's natural log 3 divided by natural log 2, still minus 2. So it's about -0.42-ish. So the x-intercept is, well, about -0.42-ish, comma 0. Okay, now, for the inverse, well, here's the thing. The x's and y's are switched, so it should be no surprise to you that the domain is going to be from -3 to infinity, because that's the range of the old one. Wow, look at that. I got it wrong. Sorry about that, folks. Let's make that less embarrassing. Boop, 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 boop. -3 to infinity. Okay, there we go. Sorry about that. All right, now, the range is all real numbers because that's what the domain was of the other one. And then, let's see, the asymptote, let's see, it's a vertical line. So it's x equals, oh yeah, it's x equals -3 because it's the x's and the y's are switched. That might be a thing. Anyway, the y-intercept, this is actually really easy. It's 0, -0.42 because it's the x-intercept, but x's and y's switched. And then the x-intercept is 1, 0, and because that's the y-intercept with the x's and y's switched. And, of course, I encourage you to look at the graph and notice, oh, yeah, that probably is right, because it is. All right, now, that's the first example. That was a bunch of fun. That's enough. Now we're going to graph logarithmic function graphs. Okay, so here we got log base 3 of x. Now, every normal log graph, it does not matter what the base is, has a vertical asymptote on the y-axis. Just like every exponential graph had a horizontal asymptote on the x-axis that then maybe was moved up or down, but began with one on the x-axis. The log graphs have a asymptote on the y-axis. Okay, so then you've got that. You've got the point, let's see here, 1, 0, because if you stick in 1 for x, log base 3 of 1 is 0. That was on the test. And then 3, 1, because log base 3 of 3 is 1, because it's 3 to the 1 to get to 3. And then 9, 2, because log base 3 of 9 is 2, because 3 squared is 9. And then, oh, this is fun. At 1/3, it's -1. Oy. Logarithms are annoying. Okay, so then, zoom, and you've got yourself a logarithm graph. Wait. That's a logarithm graph? That looks a lot like the invert. There's a thing here, folks. Okay, so we've got ourselves a log. Whoa, that was too much fun. Got ourselves a logarithm graph. The domain is from 0 to infinity. Again, not exactly at 0 because it doesn't quite get there. It's an asymptote. The range is all reals because it goes up and down forever. The asymptote is that vertical line, so it's x equals 0. The y-intercept is, wow, this one doesn't have a y-intercept. Look, it doesn't actually get to the y-axis. Now, you should be able to see this with the graph, but let's pretend you're having a bad day. So, you would go forward and you would go calculate the y-intercept because you don't know. You're like, I don't know. So, the y-intercept is when x is 0, so you stick 0 into the equation, and then you go, nope, that's not happening. There was actually a test question about this too. Okay, so log base 3 of 0 is no thank you. So that's y, symbolically. Okay, now for the x-intercept, you actually can look at this graph, and it's at 1, 0. But again, let's pretend you're having a bad day. So, okay, I got to go figure out the x-intercept. And actually, sometimes they're just not at pleasant places. So you have to do this even if you're having a great day. So x-intercept is when y is 0. So you're going to go ahead and write it instead. 0 equals log base 3 of x. Then you fret for a minute and go, I don't know. So you have to get it out of logarithm form. So 3 to the 0 equals x. And then you say, oh yeah, that's easy because 3 to the 0 is 1, so x is 1. Oh, yeah, it's at 1, like you knew already. Okay, so that's the second example. Good times. Now, on to the next one. Oh, golly gee willikers. Here's another thing, and it's been moved. Oh. Okay, so this equation is a log graph moved left 3, up 4. Again, this is a log graph. And just like every other kind of graph we've done, it's moved left 3 and up 4. I'm sorry, they haven't all been moved left 3 and up 4. Of course, I mean, in a manner similar to the way all the other graphs have happened. But this one's moved left 3 because it's added 3 inside and then up 4. And you might now look back and say, wait a minute, the other one was base 3. What's going on here? And I would gently and lovingly remind you that if there's a base is missing, that means base 10, and for most of you who remembered that, that was perhaps insulting, and so I'm sorry. So, we had a vertical asymptote at 0 for a normal log graph. So if we move it left 3, it goes to -3. Funny story, if you move a vertical asymptote up 4, like this one does, it doesn't change it. It's a line. It goes forever both ways. But it is over here at -3. And then you've got some points. There's a bunch of background noise. Now I'm sitting in a car making this video outside a hangout for cabbies and a gymnastics gym. It's a little strange. Anyway, those are the points. Now, let me talk about why those are the points. If you're talking about just the plain graph of log base 10 of x, it would be there, where that green dot is. But then it's moved left 3 and up 4, so there you have it, right? You have the point 1, 0, which is the normal great beginning point for any logarithm graph. Moves left 3 up 4, it's there. Since this is base 10, you would also have the point 10, 1 in this case, and that point also gets moved left 3 and up 4. So that's where those dots came from. The shape is the same, so there you have it. Now, domain. Domain is, it goes from -3 to infinity, which is wonderful. And then the range, and the range is all real numbers. Now there's that asymptote there at -3, so we've got the line x equals -3. Okay, yeah. The y-intercept, this one has one, you can see, and it's not going to be at a nice spot. It's going to be at 4 and ugly. So let's see here. Let's go ahead and make 0 for x. So y equals log of 0 plus 3 plus 4. Putting in 0 for x, and then you... okay, so it's log of 3 plus 4. Okay, and then throw that in a calculator, and you get about 4.48-ish. So it's the 0, 4.48-ish. So sometimes you have to do the calculations to figure out the intercept. Okay, so for the x-intercept, go ahead and you got to make 0 go for x. So, 0 goes for y. Excuse me. 0 equals log of x plus 3 plus 4. Okay, so you're going to solve. You're going to begin by subtracting the 4. So, -4 equals log of x plus 3. Now, remember, like I said earlier, there was a 10 there. So, it's 10 to the -4 equals x plus 3, since 10 was the base. And then if you subtract 3, because that's what one does to get to x in that situation, you get x is 10 to the -4th minus 3. And you might say, but Wixer, 10 to the -4th is small, and you're right, it is. It's practically 0. So this is -2.999 and 9, and that's a level of precision I don't normally care about on graphs, but it's not actually -3, and the reason why I sort of care about it here is because there's the asymptote at -3, and I didn't want it to look like it was crossing on the asymptote, because that would be bad form for a logarithm graph especially. Okay, we're making our way through. We're on the 4th example. Here we have Olin. Oh, Olin, how I've missed you. So, this one's moved right 2 and down 5. So the right and left movement matters here. It moves the asymptote, which is good, to over there. And then those are a couple points. Now, again, I cheated a little bit. So normally you would have the point here at 1, 0. Every logarithm graph starts there. But then that point is moved right 2 and down 5. So there you have it. And then this one's obnoxious. Remember, Olin is log base e. So you would normally then have a point at e, 1. If you're not rolling your eyes now, you're probably not listening. But, yep, e, 1. Okay, and remember, e is 2.718281828. My eyes are old, I don't know. But it goes forever. So it's 2 and almost 3-ish, 1. Anyway, that point gets moved right 2 and down 5. And that's where my second red dot is. Good times. So you've got your points. And you're feeling the logarithmic love. And go ahead and go down to the asymptote and go right and grow. Young logarithm graph. Okay, now the domain, well, it starts at 2. Well, okay, it doesn't really start at 2, but it tries. It starts right after 2. The range is all reals. And the asymptote, let's see, we've got a x equals 2. That's probably boring now. Let's see, the y-intercept, nope, Nope, nope. Now, again, you should see this on the graph. You would probably not waste your time, but we all have bad days, so let's pretend your day is bad. The y-intercept, you go ahead and make 0 for x, so we're talking about ln of 0 minus 2 minus 5. Okay, so yeah, ln of negative 2, natural log of negative 2 minus 5, and you throw that in your calculator because remember it's a bad day and you're already not making good decisions, and then your calculator says error because you can't take a log of a negative number. There may have been a test question about that. Oh wait, there wasn't. Oh well. So that's the y-intercept is no, leave me alone. Okay, and then the x-intercept, well, you can tell this has one and you don't know where it is. It's, you know, actually it's probably not even on the grid, so let's go get it. For an x-intercept, you make 0 be your y, and then you're looking at that, so you probably pause because it says natural log, and then you remember that really means log base e, and you don't necessarily need to write that, but you do if you look at ln and wonder why I'm doing that to you. So then you got 5 equals log base e of x minus 2, because would start by moving the 5, and then you would trade it for exponential format, so e to the 5th equals x minus 2. Oh, you can see we're getting close. X equals e to the 5th plus 2, and that's grotesque, and so it's approximately 150.41, which is somehow perhaps just as grotesque. But anyway, it's 150.41, comma 0. Yeah, that's not going to fit on my grid that goes to 10. Oh well. Hey, those are 4 excellent examples, and I know they're excellent because I made them, but that doesn't mean they're the right ones for you. So please let me know if you have any questions. Thank you for watching, and I'll see you in class.